Good morning, everyone, and welcome to my talk presenting the paper entitled From Movement Purpose to Perceptive Spatial Mobility Prediction. My name is Lisha Amici, and this is a joint work with Alintina Carnero, Mark Rovella, and Antonio Loureiro. Accurately predicting how humans move within space and time is relevant to many domains and applications, such as targeted advertising, epidemics propagation, or ride sharing. However, with the emerging requirements for privacy protection, scholars strive to tackle privacy issues when designing predictors or bypassing them by using the minimal possible data, such as conventional personal predictors. Conventional personal predictors actively rely on location data for future forecasts, such as Markov-based predictors. However, given the mobility trace of an individual, a conventional personal predictor assumes that the next location where an individual will go can be found in her set of known locations. This engenders erroneous results at each discovery of new location, which is worsened by the fact that these types of visits are numerous. A recent paper had reported that more than 70% of visits happen only once. This representative rate highlights how impacting exploration intended visits are on conventional personal predictors and put in evidence the necessity to tackle and integrate the notion of exploration when designing predictors. To tackle conventional personal predictors limits, we proposed a new exploration-aware mobility prediction framework that relies on two properties commonly observed in human mobility behavior. First, the spatial and temporal regularity. Second, when increasing the spatial resolution, exploration visits are not completely random. We propose to split the mobility prediction task into two subtasks. Purpose prediction that aims at predicting the next type of movement, whether it's an exploration visit, which means the discovery of new location, or a return visit, which means a revisit of a familiar location. In case of a return, we use the performance of a conventional predictor to forecast the future locations where the user will go. In case of an exploration, we propose to increase the spatial resolution to give an intuition on the area or zone where the user might go to. Let's start with the purpose prediction. To enable the purpose prediction, we add movement semantic to the mobility traces by associating each visit to a label, E for exploration and R for return. We assume that the first occurrence of a location in the mobility trace is an exploration, else it is a return. Following, we propose a first purpose predictor, STMP, for successive type of movement predictor, which assumption is regularity in terms of types of visits. Given the movement semantic sequence of an individual, we construct two tables, an exploration table and a return table. In each table, we save the number of successive same type of visits. Assuming the regularity, we compute the mean and standard deviation. For the prediction, given the current type, here we have R, and given the number of successive last type of visits, which is 1, if it is included in the interval defined by the mean and standard deviation of that type, then we predict the same type as we predict the opposite type. Next, we propose the second purpose predictor, i.e. IP for inter-exploration interval predictor, which assumption is exploration temporal regularity. Given the movement semantic sequence, it constructs an inter-exploration table in which each element corresponds to the interval between two explorations, which is the elapsed time. Assuming the regularity, we compute the mean and standard deviation. For the prediction, to predict the next type of movement at T next, if the elapsed time since the last exploration event is included in the interval defined by the mean and standard deviation, then we predict an exploration, as we predict a return. After that, we propose a first spatial predictor, PSP for personal spatial predictor, that takes as input the outcome of purpose predictors. In case of a return, it uses a Markov chain with a sequence of location. In case of an exploration, the spatial resolution is increased and a Markov chain is used with a sequence of zones. Following, we propose a second spatial predictor, GSP for joint spatial predictor, that similarly to the PSP takes as input the outcome of the purpose predictors and performs similarly in case of returns. In case of an exploration, it requires a global overview of the population exploratory behavior and constructs an exploration origin destination matrix in which origins correspond to locations from which users start exploring and destinations corresponds to the zones where users tend to go and perform exploration into them. After that, we want to evaluate the performance of our proposed framework. We propose to measure the exploration ratio that is defined as the number of transitions of types exploration over the total number of transitions. We also compute the accuracy of prediction achieved by a simple Markov chain predictor. We can see that individuals having a low accuracy of prediction tend to have a high exploration ratio. Second, we want to investigate whether the proposed framework is relevant to the whole population or only to a fraction of users having a high tendency to explore. We exploit mobility profiling based on exploration tendency that we proposed in our previous works that split the population into 3 groups that are scouters having a high proclivity to explore, routiners having a low tendency to explore and are constantly returning and revisiting familiar locations, and then irregulars having a medium behavior. By applying this profiling on the previous figure, we determine 3 threshold values: 0.6 that helps isolating highly exploratory users, 0.4 that helps isolating scouters, and 0.2 that roughly separates routiners from the rest of the population. After that, we use the threshold values to determine if a user is easy to predict according to her exploratory behavior, and then use a Markov chain with that user. Else, the user is considered to be hard to predict, and then we use the proposed framework. After that, we evaluate the purpose prediction performance. First, we compute the precision for each type of movement. We can see that on average, the proposed purpose predictors have a precision above 70%, which means that 70% of the time, the predicted returns are real returns. Moreover, we see that the performance are similar to the Markov chain or slightly better. For explorations, whereas the Markov chain has null scores, the proposed purpose predictors have interesting results. For the SMTP, on average, the precision is above 40%. After that, we compute the accuracy of prediction in terms of type of visits of the proposed predictors when applied to the whole population or only to a fraction of the population. We also compute the accuracy of prediction achieved with a Markov chain that is constantly predicting returns. We can see that apart from the IEIP and IEIP when applied to the whole population except routiners, that the accuracy of prediction is almost similar, with a slight predominance for the IEIP when applied to extreme explorers. We can also see that on average, the Markov chain predictors accuracy is lower than 80%, which means that more than 20% of the time, the predicted returns are not returns, but explorations. This highlights that the strategy followed by the Markov chain and conventional predictors in constantly predicting returns is a key lowering factor for the predictive performance. After that, we evaluate the performance of the PSP and compare it to the performance of the simple Markov chain predictor, Markov location oracle predictor, and the Markov zone oracle predictor that are both always correct about explorations. And the first one deals with the sequence of locations, whereas the second with the sequence of zones. We can see that on the figures that the PSP, when applied, when using different inputs and with dealing with different zone sizes. First, we can see that the PSP outperforms the simple Markov chain predictor. Second, we can see that by increasing the proportion of the population to whom we apply the proposed framework, the overall performance are improved. Third, we can see that by increasing the spatial resolution, the overall performance are improved, approaching the performance of the Markov location oracle predictor. And finally, we can see that the PSP, when taking the IEIP as input, holds the highest performance. After that, we evaluate the performance of the GSP with varying zone sizes and varying inputs. Unexpectedly, we can see that at most it performs as well as the simple Markov chain predictor. Moreover, by increasing the spatial resolution, only the minimal accuracy of prediction is improved and not the overall accuracy. This means that explorations, unlike returns, are more personal. In conclusion, exploration intended visits are important to tackle when designing predictors. The proposed framework is not greedy in terms of types of data and only require location data. Moreover, unlike traditional conventional predictors that are always wrong in predicting explorations. Our proposed framework gives an intuition on the spatial location where the user might go when exploring. Moreover, this spatial resolution can be tuned according to the requirements and needs of the using applications and services. Finally, unlike returns explorations appear to be more personal. However, we believe that there exists a relation between social relations and exploration habits. Thank you very much for your attention. I hope you enjoyed the video, and I would be happy to answer your questions in the Q&A session.